Hi, my name is Pedro Bertoletti, and today I'll talk to you about Zephyr RTOS, used as a versatile development for embedded software in ESP32. This presentation is made on behalf of Instituto de Pesquisas Eldorado. Before starting this presentation, I will give some background about me. I'm a Brazilian technology consultant focused on embedded system development and IoT project solutions development. I have more than 15 years of experience in embedded device and IoT solutions development, and also I have worked in several areas like industrial applications, low power communication, consumer electronics device development, and more. Now I'll talk a little about a company I work for, Instituto de Pesquisas Eldorado, or Eldorado for short. Eldorado is one of the greatest research institutes here in Latin America, based in four strategic cities here, which are Brasilia, Porto Alegre, Campinas, and Manaus. For 24 years, Eldorado has developed a tailored software and hardware solutions for various industries, standing as a major articulator of open innovation with projects that put Brazil on the technology roadmap. Eldorado is a world-class R&D and I provider developing state-of-the-art software and hardware solutions. It's a protagonist of open innovation, is an ERTO member and partner of innovation hubs. Here's the agenda for today. It covers from showing what Zephyr project is to a practical example showing how Zephyr RTOS can be put in action using ESP32 based project. Now, first things first, let's check what Zephyr RTOS project is. Zephyr RTOS is a Linux Foundation hosted collaboration project created in 2016. It's an open source collaborative effort uniting both corporate and independent developers from all over the world, helping build Zephyr RTOS as a small, scalable, real-time operating system. As a result, Zephyr RTOS is now an embedded operating system supported by several microcontrollers and SoCs families, like S32, for being applied in a huge variety of embedded system solutions. Here is a cut of how big Zephyr RTOS is today. It counts on more than 2,000 independent contributors. Also, Zephyr RTOS is composed by 140 repositories, summing up more than 45,000 pull requests concluded. Regarding hardware support, Zephyr RTOS is currently supported by more than 100 development boards, and it's also supported by 10 different microcontrollers and SRCs architectures, including S32 SoCs and solutions, including the RISC-V architecture. As a direct consequence of high engagement by developers all over the world, the features covered by Zephyr RTOS nowadays are really vast, as seen as this slide. As seen in Linux-based systems, Zephyr RTOS counts on high modularity. It supports advanced and bulletproof threading and memory resources management, including multiprocessor support, which makes Zephyr RTOS a very scalable and stable solutions operating system. Regarding connectivity, it is very, very vast too. It supports Bluetooth Low Energy, as or BLE for short. It's 80.15.4 compliant too, and counts on native and fully featured network stack, making Zephyr RTOS a very, very good option for Internet of Things device as an embedded OS. Regarding licensing, Zephyr RTOS has a LTS release, and it's licensed on Apache 2.0 permissive software license. So you can use Zephyr RTOS as both proprietary and commercial solutions. Now, let's take a look on how Zephyr RTOS is organized. Let's check how are the main RTOS subsystems and how Zephyr RTOS is put on. Well, First thing to learn regarding Zephyr organization, it's this block diagram, as you can see on the left side of the screen. This block diagram shows on its upper side or its upper part the most common components of a Zephyr RTOS. That is a collection of third-party libraries, application services, OS services, the kernel itself, and HAL. And on the lower part of this diagram, you can see some specific tools that Zephyr RTOS make use of to enable developers to make applications and make solutions using Zephyr RTOS. From those, I would like to highlight two of them, which is West and Bootloader. West is a Swiss arm knife of Zephyr RTOS. Developers use this West tool for almost everything in Zephyr RTOS, from preparing development environments to compile and debugging, and also flashing the target, which is, in this case, S32. And bootloader, of course, a bootloader is not a specific tool from Zephyr project, but bootloader, it's a very special topic here in Zephyr because Zephyr can use target specific bootloaders or a default bootloader. Zephyr uses MCU boot as default bootloader, but it can use, as I said before, some target specific bootloaders, as happens in ESP32. And also, regarding the build system, Zephyr RTOS uses CMake. Proceeding to the Zephyr RTOS organization topics, I would like to present some important or some very common subsystems here. As you can see in this slide, Zephyr RTOS support many subsystems, and most of it are very look-alike or is the same as you can see in embedded Linux. So you can count on debug subsystem, DFU, which stands for Device Firmware Upgrade Subsystems, Logging Subsystems, Shell Subsystems, and so on. So there's a huge variety of subsystems Zephyr RTOS can support, and you can check a little more about them on this website. Now it's time to check how a Zephyr RTOS application project is organized, okay? As you can see in this slide, an application project using Zephyr RTOS is composed by some folders and files, which is represented in this figure on the center of the screen. The first of figures I would like to highlight is the board folder, sorry. This board is mandatory and contains all project device Tre Overlays, which stands for DTO files for any specific target configurations. So it means that each DTO file can describe the hardware used for a specific target. So each microcontroller or each SoC that should run this application should have a separated or a dedicated file, DTO file in this folder. Now is the SRC folder, which is also mandatory. It contains all application source codes, which means .c, .h, .cpp files, and so on. Regarding getting deeper into the build system of Zephyr RTOS, it uses CMake, as I said before, and the CMake list file, which is also mandatory, can be found here at this structure. And this file is comprised of a set of directives and instructions describing the application's project source files and targets, which means executable, library, or both. The Kconfig file is also mandatory, and for those who are used to develop with embedded Linux environment or develop embedded Linux solutions, it works the same. So the Kconfig files here specify the application project's specific kernel configurations for this project. Also, another mandatory file, which is prj.conf, and it contains common kernel configurations that should be applied to the application project, regardless of the chosen target. So here's a point of attention. Kconfig file is specific for kernel configurations, and here is the kernel configurations that should be applied regardless the chosen target. So if you have a kernel configuration that should be applied regardless you're using a ESP32, STM32, or any other microcontroller, it should be here. And finally, here's a sample.yml file, which describes the application project features, which means the features of the project to be listed in the Zephyr RTOS contribution, okay? So this file is optional, so it's only required when there is an intention to share or to submit this project application to as a Zephyr RTOS open source official contribution. So if you are not intended to do this, you are not obligated to write a sample.yml file. Now it's time to check how device tree overlays, or DTOs for short, are used in Zephyr RTOS to offer versatility and scalability for embedded software that runs Zephyr RTOS. Well, let's start by defining what is device tree overlays, or DTO for short. DTO stands for a resource that allows developers to describe the hardware peripherals wired to the target. So that kind of peripherals that aren't self-announced, like USB or something like that, need to be described, need to be told. Kernel system, the operating system kernel needs to be told which hardware are wired to what interfaces. So DTO does this job. It contains a description of what is wired where. DTO files tell OS what pieces of hardware it must handle to. As you can see in the right side of the screen, it's an example of a node, a DTO node, that describes a SPE node, which contains a sensor, BME280 by Bosch. So this node describes that there is a sensor that should be handled by BME.80 driver, and this sensor is using SPI interface and also using GPIO 17, and pin control is related to SPO0 default, and so on. So the device tree overlay files describe the hardware wired to the target. Zephyr RTOS use DTO files to describe hardware for each target that solution must support. This is a very, very nice feature of device tree overlays, very, very nice usage of device tree overlays in Zephyr. So this very same application code can be built for multiple targets without changing a single line of application source code. So it means if you have a DTO file for each architecture that your application or your project should support, should run into, you must have a DTO file for each of them, and then only specify for which target you want to buy it or to build it, and it will be built for the specific target that you specify. This is very useful for solutions that must have as minimum production costs as possible, making it possible to rapidly and almost effortlessly port a project to another target and optimizing manufacturing costs and development costs. Well, there's a comparison between the DTO usage in embedded Linux environment and in the Zephyr RTOS development. Despite of DTO files are described and written the same way in both environments, there's a little difference on when it comes to use. I mean, in embedded Linux environment, DTO files are interpreted at boot time in a dynamic way, which means to say that if there's a bug in DTO file or some type error or something like that, it's impossible to find it out when you are compiling Linux or you are compiling embedded Linux application. So you'll find out this bug or this error only after booting the system. But in Zephyr RTOS, DTO files aren't interpreted at boot time. They are interpreted during the Zephyr RTOS compilation time. So if there are some errors or some typo or something like that, um, when you are compiling the Zephyr RTOS with these DTO files, it will raise an error or raise a warning depending on what's wrong, and you're able to find out what's wrong before booting the system. So it is very good for development, in my opinion, because it saves you time. Well, now let's check which are the main benefits that Zephyr RTOS can offer to enhance the scalability and real-world embedded software solutions. The first benefit I would like to highlight is the improvement of embedded software modularity and low coupling level achieved. Like seen in embedded Linux solutions, Zephyr RTOS is composed by a kernel, by some drivers, and a collection of software, which we call application. It works like playing Lego. I mean, everything can be abstracted like a layer or like a block, and you put everything together as your solution requires. So, uh, using the RTOS and enabling or putting some subsystems, some blocks together is like playing Lego. Okay, it makes very easy to add, fix, or replace drivers, libraries, and also very easy to change target uh, without harming or getting damage to your product as a whole. So modularity and low coupling are very, very welcome features, and Zephyr RTOS can provide it. Well, uh, the second benefit I would like to highlight you is the scalability and versatility that Zephyr RTOS can offer. As said before, if you have a DTO file for each architecture or each target your solution must support, you can develop a target agnostic solution, which means the application codes is the very same and doesn't depends or doesn't make references to the target, to the deep target features. So you can modularize and how can I say isolate the hardware specific features from the application. So having target specific files for each microcontroller or SoC, as I said before, um, using this, it's possible to build the embedded solution for any supported targets you want without changing a single line of application code. It's very, very nice, and it saves you a lot of headache when porting products from another architecture or another SoC. Well, the third benefit of using Zephyr RTOS is it's open source. Zephyr RTOS is a big and very active open source project, as we've seen in the beginning of this presentation. It's a huge project right now. So it means to say it's constantly being improved or constantly being fixed too. And new features from Zephyr RTOS comes out every day. And developers count on a community support, a very active community support, by the way, for asking questions, discussing bug fixes, um, making questions, and so on. So Zephyr, it's a very, very friendly for developers because it's open source and it's very, very competitive. You can count on people to help you from community if you need. Zephyr RTS also have a long-term stable, which or LTS for short version. What's perfect for using it in products that should be manufactured or sell for years. So it adds reliability and also quality to the embedded software as long as you have a long-term stable version available. The next benefit I would like to highlight is that Zephyr uses a permissive open source software license. Zephyr RTOS is licensed under Apache 2.0 software license, which means it's a permissive open software license, allowing both commercial and private use. So as Apache 2.0 isn't a copyleft software license, you have this flexibility or this easier easiest to make it usable for commercial products. Okay, so if you want to develop something to sell, if you want something to build your own product, you can use Zephyr RTOS without having headaches regarding licensing and sharing some private or some how can I say, some not public code. You won't suffer from that. Therefore, developers and embedded software companies can use Zephyr RTOS in their products. Okay, so it's good to sell, good to use in real world products, and so on. Now let's go on. Now let's see the source code of a full project that use Zephyr RTOS as an embedded operating software. Let's check in this case, a LoRaWAN tracker that uses Zephyr RTOS as an embedded operating system using ESP32 WROOM32 as a microcontroller or as a target. Before going to the code overview itself, let's check some requirements. Before proceeding to try to reproduce this project in your machine, I would like to give you two requirements or 2 points of attention that you should follow. Okay, the first one is you should prepare your RTOS, Zephyr RTOS environment by following the getting started guide, depending on your operating systems in your host machine, like Windows, Linux, or Mac OS, and this website. So in the Zephyr official website, you can get a getting started guide to set the Zephyr RTOS environment on your machine. And also, you can download the project source code of this project we are presenting you in this URL. And so you can get software, you can change it, you can contribute to it. Feel free to use it. So it's up to you what you do with it. So very important, ensure your downloaded project, which means the GNSS LoRaWAN tracker project, is located into your Zephyr RTOS environment folder, which means per default in Zephyr project / Zephyr folder. Okay. Giving some features of this GNSS LoRaWAN tracker we are talking about, it is a GPS / GNSS tracker using ESP32 WROOM. It obviously it can get the coordinates, latitude and longitude, and also it monitors the ignition input from the board. So it simulates a vehicle. So when you turn the vehicle on, it can get the input, the ignition input, we turn it off, and so on. As connectivity, it uses LoRaWAN by using a LoRaWAN module. It's manufactured by a smart modular manufacturer. Okay. Controlled by AT commands using a WART interface. We'll see more about a little later. Regarding what this project does is it periodically sends the coordinates, latitude and longitude, and also in the same package, it sends a tracker status byte, where bit 0 means ignition status, which is 0 for off, 1 for on. Bit 1 has the GNSS fixed status, which is very important to determine if the coordinates you are getting is reliable or not. And I'm not using the another 6 bits in the byte. So from bit 2 to bit 7, it's reserved. Now it's demo time. Let's check how code works. I'm opening the code here, the full source code in Visual Studio Code. Okay, so I will start by the boards folder. As I said before, boards folder contains all the DTO files or DTO overlay files that must describe the hardware for each target you are using. In this project, we are using only one target, which is S32W room. But if you have more targets, you can describe their DTO files into this folder, boards folder. Well, this file starts by defining some aliases, okay, to GNSS, to lead zero, which is a briefing light, a light that periodically blinks, indicating this embedded software is working, okay, and the ignition, which here is interpreted as a button, okay. So Zephyr RTOS sees the ignition as a button, okay. And you can see it here in the buttons node. Okay, ignition is described as an input key 1 button, and it's using GPIO4 from S32 level room. It's pulled up and active low, and its label its ignition signal. Okay, so to sum up, Zephyr RTOS will see this as a button. Regarding the LED, the briefing light LED, it's wired to GPIO 18. It's active high, and its label is briefing light. Okay, so its LED it's has only one purpose: blink when software is working. Okay. Now let's start the UART definitions, which means the communication to the GNSS module, which uses an NMEA2 protocol and by using a UART interface. So UART1 from S32W room is used to communicate to this GNSS module here. And I'm using STX pin, the GPIO 25, and RX pin, the GPIO 26. Okay, and for communicate to the LoRaWAN module, as I said before, via AT commands and UART interface, I'm using UART2 from S32 double room and GPIOs 23 and GPIO 5 STX and RX. Still regarding the UARTs, okay, I defined its baud rates and in these nodes here, WART1 and WART2, and also for GNSS module, there's a special subnode here into the WART1 node that defines which driver should handle the data received from WART1, which is the GNSS NMEA generic driver. So everything that comes from WART1 coming from the GNSS module will automatically handled by the GNSS NMEA generic driver. And so it can export the needed files and the needed control status and so on to read the GNSS or GPS module coordinates and status. Well, the first file to get deeper to is the main.c file, which is here in this project, the first .c file that should be run. Okay, so on its main function, it's very straightforward. All it does is to start every module here in the software, which means briefing light module, ignition monitor module, LoRaWAN module, and GSS manager module. And if some of these modules doesn't work or doesn't start or present some error, the log error message is presented, or a message indicating it's all good is presented. The simplest module here is the briefing light. Everything it does is blink light every time defined in this macro, which is 1 second. So from second to second, the light, the LED are wired to the briefing light pin. It's turned it on and turned it off. It's still good. And this is done by a thread, okay, Zephyr thread, which is created using a K thread, and their parameterizations like um, priority and so on. It's defined into a Kconfig file, which we'll see a little later. And another important part here is that the informations from LED, it's loaded from is directly from the DTO files by using this macro here. So when you declare a GPIO DT spec and use this macro, it will read from the DTO file for your target, which is the LED 0 underscore node alias, which means LED 0 alias. So in this line, the compiler goes back to the DTO file, try to locate a LED 0 node and load its parameterization here into this variable. Okay, so that's why the DTO file is interpreted during the compile time, not during dynamic by the boot time. Moving on software, here we have the ignition monitor, which monitors the ignition status and check if it's on or off, and also applies debouncing routines to register the right ignition on and off without bouncing on off on off on off all the time. So it uses a K timer, which is a timer, software timer from kernel here. And when the ignition status changes from 0 to 1 or 1 to 0, ignition level, sorry, it starts a timer. And if the timer reaches its end without being restarted, it means the bounce is over. So when it happens, it calls this callback. And by this callback, I can get the uptime, the timestamp now, or uptime when it has been detected, and reading the pin, the ignition pin, to get its final state. So after bouncing, if its final state is 1, it means the ignition is on. By after the timer time gets ended and the ignition level it's 0 or low, it means the ignition is off and goes on. Okay, so the ignition monitor module init, it starts the ignition GPIO, it configures and everything as said in DTO file, and from this point on, everything is done by interrupts. Here, proceeding to the software, we have the LoRaWAN UART module, which handles the smart modular LoRaWAN module. In this module, as I said before, is smart modular LoRaWAN module uses UART communication, okay, using AT commands. So every function here that handles that exchange data with this module, it's in fact formatting and sending and receiving AT commands, okay? So we'll get into a little later, but everything it does is to format an AT command and send and get its response. So the initialization of the LoRaWAN module is nothing but running every single command here to send the AT commands to start, wake up the module, set the LoRaWAN credentials, the join mode, and so on, everything regarding LoRaWAN, and also getting it ready to work. But if you see a little deeper, everything it does is to format AT command and send it using LoRaWAN words. And if you can check this function here, the function that sent the AT command, it everything it does, it just send the command, and there's a function to receive response for modular LoRaWAN module. So it's very straightforward. Moving on to our last module here is the GNSS Manager module, which handles all the GNSS messages received and already parsed from NMEA protocol by using the callbacks. So everything that comes from GPS and GNSS module is read by the GNSS driver, as we said in DTO file explanation before, and the driver parses all the data and raises the callbacks. So when the callback here is called, it gets the parsed data by this GNSS underscore data struct. So what I need to do is to check if there's a fix in GPS, and if so, I can adjust the latitude and longitude value by dividing it by this constant, indicating in the logs that it has a fix. And this value here, less latitude, less longitude, these variables are global variables here in this software. So I can access it in another function and get the less latitude and less longitude read from GNSS and GPS module. So after the initializations, everything is handled by a thread, okay, as a dedicated thread. And in this case, every second, this loop is running in the GNS thread and checking the less latitude and less longitude that it has been read, and it sends it to the LoRaWAN module by using this function, send tracking data. So the LoRaWAN can send it to the cloud. Correction, this time is the uptime, the time that a position or a packet is sent from this device to LoRaWAN. In this case, it's set to 15 minutes. So every 15 minutes, the last latitude, last longitude, and ignition status are get and sent to the clouds via LoRaWAN. As I said before, the Kconfig here looks very like in the Linux environment. If you develop Linux environment solutions, you recognize it. So it's very, very straightforward, and every config here can be accessed, it can be obtained or read into each module, and so on. The CMake list file has no mystery too. The only point of attention here is to not forget to declare or to use each source file you need to build. Okay, so these are the main.c file plus each module .c file, and I will show you after you send it to the clouds, you have a 9 bytes chunk of data package, and which the 4 first bytes refer to latitude, the 4 next bytes refer to longitude, and the last byte refer to the ignition status and fixed status. In this case, fixed status is 1, okay, GPS is okay, and ignition status is 0. Just to be clear, this one is here is the fixed status, and this last bit 0, and the last 0 is the ignition status of this example package. Okay, so if you can check here in the terminal, I will restart the application. I have this project wire here. So Zephyr started. It's configuring LoRaWAN module. It already sees 11 satellites here, and it has a fix. And every 15 minutes or 900,000 milliseconds, it sends the coordinates and also the ignition status to the cloud. I will change the ignition status here. As you can see, ignition is off. I changed it again, ignition is on. It's already debounced, so everything works as expected. So as we finish the demo, I would like to show you the references used for make this presentation, which are the Zephyr project website, Zephyr RTOS GitHub repository, and block diagram get from the NXP documentation, and also some embedded LabWorks slides from embedded Linux course, as you can see in this URL. I would like to thank you all for watching this presentation. I hope it was helpful. And if you have some questions, please reach me at Q&A session. See ya.